So we've seen how to count up a number of possibilities when you aren't replacing the items and the order that you choose them in does matter. But what about situations where the order that you choose them in doesn't matter? This is actually pretty common. Just for one example, imagine choosing a 5-card poker hand from 52 cards. How many ways are there to do this? Would that be 52 permute 5? Well, it turns out, no, that's not right, because permutations keep 52 permute 5 keeps track of what order you choose the cards in. But for a poker hand, the order that the cards are in doesn't actually matter. So just for example, in a poker hand, if you draw all diamonds, if you draw the 2, 3, 4, 5, and 6 of diamonds, is that a different poker hand or the same poker hand as all diamonds 6, 5, 4, 3, and 2? Well, these are actually the same poker hand. So for poker hands, order doesn't matter. But this permutation trick does keep track of order. So what should we do to to count the number of poker hands where order doesn't matter? Well, one way to approach it is first count up the number of ways of getting a 5-card poker hand out of 52 cards, including the order, and that would be 52 permute 5. So that we already have a formula for. This one is 52 factorial divided by 52 minus 5 factorial. But we've counted each possible poker hand multiple times. For example, this permutation calculation counts these two poker hands as different, even though really they're the same. So how many times have we counted each poker hand? Well, if you draw 5 cards, every different way of arranging them counts as a different permutation. So what we really need to know is how many ways are there to arrange 5 cards once you've chosen which 5 cards are in the hand. But that's just, there are 5 ways to choose the first out of the 5 cards that you have. There are 5 choices for which to put first, 4 choices for which to put second, 3 choices for which to put third, 2 choices for which to put fourth, and then for your last card, there's only 1 left, so there's only 1 choice there. And so that's 5 factorial, which happens to be 120. So this is the number of ways to arrange the 5 cards in your hand. So we've counted by finding 52 permute 5, we've counted every possible poker hand 120 times. So all we need to do is take the total number of permutations and divide it by the number of times we've counted each hand, which is 5 factorial. So 52 permute 5, that's 52 factorial over 52 minus 5 factorial. Just divide that by 5 factorial. You can rearrange the fractions like this. It's 52 factorial divided by 52 minus 5 factorial times 5 factorial. And if you put this all into a calculator, you get 2,598,960. So quite a lot of poker hands. But this is far fewer poker hands than if you counted order, if you decided that order mattered. So let's see how this works out in general. If you choose R items from N items, an order doesn't matter. So it turns out that this formula we got, or this way of calculating this that we used on the last slide, where we got 52 over 52 minus 5 factorial times 5 factorial. The same argument, but using N and R instead of 52 and 5, still works, and it gives you this formula. N factorial over N minus R factorial times R factorial. This is written N and then a capital C and then a subscript R. And it's a capital C because you're choosing instead of permuting. So that's why the capital C. And this is read N choose R. Notice that this formula really only makes sense when R is between 0 and N. It could be 0 or N, but you can't have R be negative, and you can't let R be bigger than n. And the reason for that is if r were negative or bigger than n, in the denominator here, you'd have a factorial of a negative number, which it turns out a factorial of a negative number is defined, but it's not what you want in this situation. So this formula only makes sense if r is between 0 and n. Now, if you tried to calculate this, this 52 choose 5 just by putting the factorials into your calculator, it would probably complain. The number that you would get from this factorial is just way too big for the calculator to handle. Fortunately, most scientific calculators have this function, n choose r, built into it somewhere. Usually it's a shift function on one of your number keys. So on my calculator, for example, shift 3 is the n choose r button. So to calculate 52 choose 5, on my calculator, I enter 52 and then shift 3, because that gives me, on my calculator, shift 3 is n choose r. And then I enter the 5 and then hit equals. I'm not actually adding these, I'm just and hitting these buttons. And that's how I got the giant number in the last slide. So just to see that this formula really is working, let's do a few quick sanity checks on this formula. So let's use this formula to figure out how many ways there are to choose no things from 5 things. Now the reason I'm calling this a sanity check is because we already know how many ways there are to choose no things from 5 things. How many ways of choosing nothing is there? Well, there's only one way to choose nothing, and that's to not choose anything. So what we should get for this one is 1. So now let's use the formula and see if we actually get 1. So choosing no things from 5 things, this would be 5 choose 0. So this would be 5 factorial over 5 minus 0 factorial times 0 factorial. So this is 5 factorial over 5 minus 0 is 5, so 5 factorial. And remember, 0 factorial is 1. Mathematicians agree. This is really why 0 factorial needs to be 1. It's so that this formula will work. And then the 5 factorials get simplified, and you're just left with 1, which is what we were supposed to get. So the formula does work in this case. All right, let's look at another example. How about choosing one thing from 5 things? Again, in this particular example, we know what we should get. If you have 5 different things and you need to choose one of them, how many choices do you have? Or how many possible choices can you make? Well, you can make 5 possible choices. You can choose the first one, the second one, the third, the fourth, or the fifth. So we should get 5 out of this n choose r formula. So let's try it. The number of ways of choosing one thing from 5 things, that should be 5 choose 1. So that's 5 factorial over 5 minus 1 factorial times 1 factorial. So this is 5 times 4 times 3 times 2 times 1. 5 minus 1 is 4, so 4 factorial, that's 4 times 3 times 2 times 1 times 1 factorial, which is 1, and then simplify, and you're left with 5. Good, that's what we were supposed to get. All right, now let's try this, choosing 4 things from 5 things. In this case, it's a little harder to see what we should get, but choosing 4 things from 5 things is actually the same as what you're really doing is choosing them all, but then discarding one. And so you just have to choose which one is the one that you discard. Well, there are 5 choices for the one thing that you discard, and so there are 5 different ways of choosing 4 things. All right, now rephrasing this in terms of n choose r, we have 5 choices, and we're going to choose 4 of them. So this is 5 factorial over 5 minus 4 factorial times 4 factorial. Now the numerator is 5 times 4 times 3 times 2 times 1 again. 5 minus 4 is 1, so 1 factorial. And then 4 factorial is 4 times 3 times 2 times 1. And again, so much simplifies that we just get 5. So that works out. And for the last sanity check, let's see how many ways there are to choose 5 things from 5 things. This is supposed to be a 5 here. And again, in this case, we know what we should get. If you're presented with 5 options and you have to choose 5 options, well, there's only one way to do it. You have to choose everything. Okay, but the number of ways of choosing 5 things from 5 things, that should be 5 choose 5. And according to our formula, that's 5 factorial over 5 minus 5 factorial times 5 factorial. The 5 factorials cancel, and you're left with 1 over 0 factorial, but 0 factorial is 1, so we do get 1. So you can see in all of the cases where we have some good intuition about what this formula should produce, this formula does give us the correct thing. So now that we trust this formula a little bit, let's see what we can do with it. Here are a few examples. How many ways can you choose a relay team of 4 runners from a roster of 7? If we're just choosing the team and not choosing positions, then it doesn't matter what order you make your choice in. So this would be a job for n choose r. So we have 7 possible choices, and we need to choose 4 of those. So we get 7 choose 4. So that would be 7 factorial over 7 minus 4 factorial times 4 factorial. This one is maybe just small enough that we could do by hand. So 7 times 6 times 4 times 3 times 2 times 1. And I missed my times 5 in here. And then in the denominator, 7 minus 4 is 3. So 3 factorial, that's 3 times 2 times 1, times 4 factorial, which is 4 times 3 times 2 times 1. Now we can simplify this. But also, we can simplify a little more because 3 times 2 is 6, so that simplifies the 6. And we're left with 7 times 5, which is 35. So there's 35 different ways of choosing our running team. Second example, suppose that we are running a sport ball tournament that has 10 teams. How many different head-to-head matches could we run? So I guess we need to decide what we mean by a match. And this is when one team plays against another team. So to get a head-to-head match, you actually need to choose 2 teams. And it doesn't matter what order you choose them in, because if team 1 plays team 2, that's the same match as if team 2 plays team 1. So order does not matter here, and so we can use n choose r. We have 10 possibilities. We need to choose 2 of them for a match. So this is 10 factorial over 10 minus 2 factorial times 2 factorial. So 10 factorial, that's 10 times 9 times. Now, we could write 8 all the way down to 1 here, but 8 all the way down to 1, that's 8 factorial divided by 8 factorial times 2 factorial. The 8 factorial cancels. Also, 2 factorial is just 2, so we can simplify this 10 down to a 5. 5 times 9, that's 45. So there are 45 different matches that we could run in this tournament. All right, third example. If we have a classroom that has 20 desks and 20 chairs, but I only need 10 desks and 10 chairs for my class, how many different ways can I choose desks and chairs? And just for this example, let's not worry about which chair goes with which desk. Let's just choose the desks and chairs and not pair the chairs up with the desks. Okay, so we need to choose some desks, and we need to choose some chairs. Okay. for the desks, it doesn't matter what order you put the desks in, and so we can use n choose r. We have 20 possible desks to choose from, and we're going to choose 10 of them. We can't choose any one desk more than once, because once you've chosen it, that's it. So 20 choose 10. For the chairs, well, look, we also have 20 chairs, and we're going to choose 10 of them. The choices we make for the desks doesn't have any influence at all on the choices we make for the chairs, so these are independent choices, so we can just multiply these numbers together to get the total number of possibilities. So 20 choose 10 times 20 choose 10, that's 20 choose 10 squared, which you can imagine is going to be a pretty big number. In fact, it's so big that I'm going to use a calculator for this one so that I don't have to do all the multiplying out while you're watching. So 20 choose 10 is 187,756. And now we need to square that. So that is 34,134,779,536. So there are lots of different ways to choose chairs and desks for this class. All right, let's figure out how many 5-card poker hands are a full house. So in other words, how many full houses are there that we could possibly draw? If you don't know, a full house in poker is a pair and a 3 of a kind in one 5-card hand. One way to think about this sort of problem is to think about all of the choices you would have to make to build a full house in your hand. So the first thing you would have to choose is you'd need to choose a rank for your pair. The next thing you would need to choose is a rank for your 3 of a kind. Okay, once you've chosen a rank for your pair and a rank for your 3 of a kind, well, for the pair you need to choose which 2 cards of the rank for your pair. So you need to choose 2 cards for your pair. And then you need to choose which 3 cards for your 3 of a kind. Now, for each of these choices that we need to make, what we chose for that earlier choice doesn't affect the number of possibilities for the later choice. It does affect which possibilities are still available for a later choice, but it doesn't affect how many choices there are. So once we know how many possibilities there are for each of these choices, we'll be able to just multiply together all of these possibilities. So how many ranks are there to choose from for forming our pair? Well, there are 13 ranks total, and they're all still available to choose from, so that's 13 possibilities. All right, now how many ranks are available for our 3 of a kind? Well, we have chosen one rank to be our pair, and we can't choose that rank again, because if we had a pair and a 3 of a kind, that would be 5 cards of that rank, but there aren't 5 cards of a single rank in a regular 52-card deck. So we can't use the same rank for the 3 of a kind that we chose for the pair. So there are only 12 ranks left for our 3 of a kind. All right, now that we've chosen a rank for the pair and the 3 of a kind, we need to choose for the pair which 2 cards are actually in the pair. We have to be a little careful here. We might choose, say, the 2 of hearts and the 2 of, that's the 2 of diamonds and the 2 of hearts. Or a different choice we could make is the 2 of hearts and the 2 of diamonds. Are these different choices? No, these are the same choice. It doesn't matter which order you put them in. And so that means we aren't going to use permutations, we're going to use choose. So n choose r. And for the single rank that we've chosen for our pair, there are 4 cards in that rank, and we need to choose 2 of them. So 4 choose 2. By the same token, for choosing the 3 cards for a 3 of a kind, we're going to use choose, and it's 4, choose 3. All right, now we can just do all this arithmetic. So 13 times 12 times 4 choose 2, that's 4 factorial, over 4 minus 2 factorial times 2 factorial, times, and then 4 choose 3, that's 4 factorial, times 4 minus 3 factorial, times 3 factorial. So 13 times 12 times 4 times 3 times 2 times 1 over 4 minus 2 is 2, so 2 times 1 times 2 times 1 times, and then for our last quotient, 4 factorial, so 4 times 3 times 2 times 1 over 4 minus 3 is 1 factorial times 3 factorial, which is 3 times 2 times 1. Now we can do some simplifying, so this 2 times 1 cancels that one. This 2 simplifies this 4 down to a 2. In our second quotient, 3 times 2 times 1 all simplifies away. So we're left with 13 times 12 times 2 times 4. And then we can do that calculation. So 13 times 12 times 2 times 4. That's 1,248 possible full houses. This might seem like a lot, but remember, there are millions and millions of possible 5-card hands, and only 1,000 of them are full houses, so pretty rare.